All right, I think we can get started. For those of you who don't know me, I'm Elliott Rouse. I'm a professor in the Mechanical Engineering Department in the Robotics Institute, and I direct the Neurobionics Lab where Alejandro has been studying for the last 5 years. So welcome to Alejandro's dissertation defense. I attended a presentation recently where they mentioned kind of one of the benefits of a virtual defense is that it allows like many different people to attend from all over, which I think is kind of a nice silver lining, and it's great to see everybody. We have a big group here. First, I'd like to kind of personally recognize and thank Alejandro's committee, Doctors Greg, Moody, and Vasudevan for their valuable insights throughout Alejandro's project. For the ground rules, in a moment, Alejandro will present his doctoral research. We should hold questions until the end. After the presentations, audience questions will be answered, and then the committee and Alejandro will break off to a separate room where we'll continue to ask him questions for a short while after that. Before we get started, I kind of wanted to take just a second and tell you a little bit about what it's been like working with Alejandro over the past 5 years. And what I've been really impressed with is that Alejandro just gets it. So he gets technical concepts with ease, design, mechatronics, perception, and you'll hear about these in a few minutes. He's been awarded basically every fellowship or award I can think of, including best paper competitions, best demonstrations, the NSF fellowship, the Rackham Predoctoral Fellowship, and the list goes on. But what you won't hear about, and what I've observed over those years, is that he gets it all. He gets how to communicate and be gracious with our collaborators when they're contacting him with questions about the open source leg every other week. He knows how to work with patients and makes them feel comfortable while he's tuning their control system. And he gets how to be a strong leader and a teammate in both the lab at Michigan, but also at the team at Google X. And I guess all this to say that I'm really proud of Alejandro and the scholar and colleague that he's become, and he will be missed dearly. So also I'd like to encourage you to ask the hardest questions you can think of and save that to the end. Without further ado, Alejandro Azocar.
All right, everybody, thanks for coming. I'm excited to kind of share the work that I've been doing for the last 5 years, looking at design, control, and perception of different types of bionic systems. Thanks everybody for being here. Thank you to my committee, and really start to get everybody on the same page to talk a little bit about what bionic systems are. So for this talk, bionic systems are robots that you can wear, and they either replace, they assist, or they interact with your body. And in particular, I've been focused on lower limb bionic systems, so systems that help you walk better and walk faster. And most of my work over the past 5 years has looked at bionic prostheses. So these are mechanical devices that replace missing limbs. And I've also done some work with bionic exoskeletons, which are devices that go over your existing limb. And most of the work that I'll be presenting is going to focus on prosthetic legs, but the nice thing about these systems is that they share a lot of similarities in terms of control, in terms of the types of hardware and software constraints that they have. So although a lot of those things that I'll be talking about will be focused on prosthetic legs, many of those things still apply to exoskeletons. The reason I'm super interested in prosthetics is because in the US alone, there's millions of people with lower limb amputations. And these people in general, they walk slower, they get tired faster, they fall more often, and they develop biomechanical walking patterns that over time lead to other issues like osteoarthritis, osteoporosis, and back pain. And in addition to these physical impacts, they also have unseen social impacts. So there's social stigma related to having an amputation, and there's higher rates of depression and unemployment. And part of the reason why these physical impacts occur is due to the passive nature of prosthetic legs that most people wear. So on the right, on the top, we see a prosthetic knee, and on the bottom, a prosthetic ankle. And the systems that you can normally purchase if you're an amputee are passive, meaning they behave like dampers or like springs. And what I mean by passive system, I mean that these systems can't generate positive mechanical energy. A spring, for example, can store and release and return energy, but it can't create energy. And similarly, a damper can dissipate energy, but it can't generate energy. And this is in direct contrast with what the human body does, because we have muscles that can actually generate energy. So for example, at the knee, when you're walking upstairs, the muscles around your knee help it generate about 50 joules of positive work during walking upstairs and during walking on level ground, the muscles around the ankle generate about 20 joules of positive work. And so the fact that these passive systems can't generate any of this positive work leads to amputees having to create different biomechanical patterns of walking. So you can see here, walking up the steps, they have to swing their leg around to help get up to the next step. And also when you're walking on level ground, amputees generally tend to have to use a lot more hip motion to compensate for the fact that they don't have this power to push off. And that's where bionic systems come in. So bionic systems have batteries and motors that can generate positive power. And really the age of bionic systems began about 15 years ago at MIT and at Vanderbilt University. So on the top right, we see a series of bionic ankles that have been developed at MIT. And on the bottom, we see a couple different iterations of bionic legs that were developed at Vanderbilt. And so when I say a bionic leg, I mean both a knee and an ankle system, so a full leg system. And over the years, both of these groups have done a lot of work in terms of studying how to design these systems, how to control these systems, and particularly with the powered ankle system, it's been shown and through multiple research studies that a bionic ankle can help restore metabolics, walking speed, and biomechanical walking patterns in amputees to be closer and to be a lot more like what a normal person without an amputation walks like. And this is a little bit harder to accomplish on a full leg system because in addition to missing an ankle, you're also missing a knee. So now you have more challenges in terms of you have to control and coordinate multiple degrees of freedom. You have more weight to carry with a prosthetic system. And then there's additional safety challenges related to if you make a mistake with the knee could buckle underneath you and you could fall and injure yourself. Now I'd like to give a big picture overview of how these bionic systems are typically controlled. And this is very similar for both prosthetics and exoskeletons that we tend to split control into three hierarchical levels that all feed into each other. So at the highest level, what the controller needs to do is figure out what does the person want to do. So the bionic leg or the exoskeleton needs to know what the person is trying to do. And the state-of-the-art way to do this is when we collect sensor data. So that sensor data can come from the bionic leg itself or from the person. We feed it in through a machine learning model or a heuristic hand-tuned model. And we use that model to predict an activity. And when I say an activity, I mean, is the person trying to walk on the level ground, trying to go up, down ramps, or up and down stairs? And so once the high-level controller has figured out what activity the person is trying to do, the next step is to send that information to the mid-level controller. And the role of the mid-level controller is to take, for example, if somebody's trying to walk on level ground, is to take that activity and generate the best possible form of assistance. And this assistance usually takes three different forms of control. One is position control, where you're actually commanding the position of the bionic leg or the exoskeleton. Torque control, where instead of commanding positions, you're commanding the torques and the forces that the device produces. And finally, sort of in between position and torque control is impedance control. And I'm going to focus a lot on impedance control throughout this talk, so I'll kind of dive into that a little bit more later. And finally, once this mid-level controller has decided what is the best way to assist somebody for walking up stairs or walking up ramps, then that mid-level controller sends the desired actuation to the low-level controller, which actually makes sure that this assistance is produced on the motor. And this involves more traditional low-level control like feedback control and feed-forward control. And one thing about these different control levels is the field has really focused on the mid-level control. So how do we best choose a position profile or a torque profile or impedance parameters? And the field has created many different ways of doing this. For example, some groups do optimization. So optimizing the torque profiles to reduce metabolic cost, or sometimes we do neuromechanical models where we're trying to model what the human body does with muscles and create torque profiles based on that. But in many cases, we end up doing hand-tuned heuristic controllers where we're just tuning profiles and parameters until we find a pattern of assistance that helps the most. And high-level control has, in the last couple of years, started to grow a lot in terms of research with the growth of machine learning and artificial intelligence. But the field doesn't really focus too much on low-level control because that's an area of control that has been studied for decades, both in robotics and outside robotics as well. Now, although the field as a whole has has made tremendous progress in the last 15 years. There's still lots of challenges left to make a real meaningful impact with bionic systems. And I kind of like to divide these challenges into 3 areas. One is hardware, another is controls, and the last is the user perspective. And from the hardware side, the biggest issue is mass. And honestly, kind of all of the other issues, for the most part, they somehow relate to mass. So a robotic system is heavy. You have to carry the mass of the leg, of the motors, of the batteries. For example, a bionic leg that is available to buy in the market is 4 to 8 times heavier than passive ankles. So there's a huge increase in mass with these systems. Another issue is that a lot of these systems that use torque or impedance control don't actually have a torque sensor on them because torque sensors are heavy and they're big. So what a lot of people end up doing is they either use springs as a substitute for torque sensors, or they just don't use torque sensing at all, which leads to some of the control issue that we end up doing open loop torque control or closed loop current control. And the issue there is that in many cases, we don't actually know that the output torque of the bionic system is what we want it to be. And another issue is I showed that hierarchy earlier of high, mid, and low level control is that many groups only focus on one of these levels of control. So only focus on mid-level control or only focus on high-level control. And there are very few groups that really span the range of control. And so there's not really a seamless transition and seamless communication between different levels of control. And finally, from the user perspective, there's been, over the last 15 years, a huge push and a huge focus on the actual bionic systems themselves, and less so on the user side and on testing, lots of testing with users. For example, lots of groups spend years developing bionic systems. They run one study, publish one paper, and that's it. There's no follow-up, there's no continual improvement of testing with users. And in addition, there's been very little work to understand, especially on exoskeletons, how do people respond to assistance and how do people perceive assistance? So the work that I've done over the past 5 years is attempting to start to address a lot of these issues. And I did this in 3 parts. So the first part is designing an open source bionic leg. The second part is characterizing open loop control in these bionic systems, so characterizing it and improving on it. And finally, looking at the user side, looking at how well people can perceive changes in the properties of these exoskeletons. So this work is a combination of technical improvements in device development as well as scientific exploration. And there's a lot of work in between these 3 studies. So I'm going to mostly give a high-level overview of all of these, but feel free to ask questions and I can dive in anywhere. So to start off with the open source leg, this has kind of been the biggest push of my PhD over the last 5 years. The goal here was to really create a system to unify the field. And we've done this part through the actual design, but also through publications and through dissemination to the public. And so I presented this a couple years ago at a biomedical robotics and mechatronics conference, where I came in as a finalist in the student paper competition and best hardware demo. And last month we were finally accepted into Nature Biomedical Engineering. So it was really exciting to have a robotics paper in a biomedical engineering journal. I mean, I would like to say that the open source leg, or the OSL, I might call it OSL during the talk, has been a huge collaborative effort. So I had the privilege of leading this project, but in terms of the design, there were a lot of people involved. Elliott, for example, as well as Luke Mooney, who's on my committee. And we also had Tom Sharkey in Chicago, who we all helped to actually design the system. So as I mentioned before, MIT and Vanderbilt kind of got started in the field of bionics, but since then, a bunch of other groups have started to work in bionics as well. And here's just a couple examples of different systems out there. And the issue with bionic systems, one of the biggest issues is that it takes a long time to actually get a bionic system working. So it has a huge requirement of resources, both in time and money, before people can even begin doing research. And even once the research is done, all of these devices have very different mechanical properties and mechanical performance that is hard to compare between research groups, the pros and cons of different devices and different control systems. And also many of these devices have to be tethered to a power supply or to a computer, so they really can only be tested on a treadmill or in a closed lab setting. So there's a lot of comparison challenges here. And another challenge is that there's a lot of, especially in the last couple of years, there's a lot of groups who are doing machine learning or who are doing a lot of modeling that want to test their system, their models and their systems on an actual robot, but they don't have necessarily the resources or the desire to build a system themselves. So kind of the goal of the open source leg is to begin to unify the field with a common hardware platform and to allow new researchers to also come into the field. And so here's a picture of the open source leg, and we designed it with trying to stick to these 5 principles as much as possible. So we want the leg to be simple to use, simple to assemble, and simple to control. We want it to be portable, like I mentioned before. We don't want to be tied to just a treadmill. We want researchers to be able to take this out into the world and into the home and really test these systems, test their controllers, and make meaningful improvements. We wanted it to be scalable so that people could use just the ankle or just the knee, or use both. So this is both the knee and the ankle work really well together. We also provide some customization options, which I won't dive into too much during this talk. And we also wanted to make it as low cost as possible. And one of the highlights of our system is the motor that we're using. So historically, bionic systems have used this kind of motor, which is long and skinny. Instead of using this type of motor, we're using this motor, which is short and has a much bigger diameter. And the reason we're using this motor is because it has a much higher torque density. So these motors were originally developed for the drone industry. And because drones can't use transmissions, they have to produce a lot more torque. So the main difference between this motor and the motors that previous prosthetic legs use is that this operates at high torque, low speed regimes, whereas previous motors operated at low torque, high speed regimes. But in some of my early modeling, I showed that with this motor and a lower transmission ratio, we can be approximately 4 times more efficient than with the other motors. And one thing I'll point out is that with this motor, we teamed up with a company called Defy, that's led by Luke Mooney, one of my committee members. And they provided the electronics and the low-level motor controller that's open source to help us control the system and to help others control the system as well. Now, I won't go into too much detail on the actual design, but I want to give an overview of the design process. So the way we went about designing this leg is, first we started by understanding the biomechanics of human walking. So we wanted to study what forces and speeds and torques and positions does the human knee and the human ankle go through across many activities. So we built a model of this, a computer model of this. And then that model allowed us to create a model of what a motor and a transmission would have to do to accomplish those speeds in the prosthesis. So this was using traditional motor equations and transmission equations where we simulated different transmission ratios, different motors, and different springs. And then this model can also be applied to go from mechanical constraints to electrical constraints as well. So we start from the human body and we end with what does the motor have to do in terms of commanding voltages and currents. And really ultimately what we care about is the thermal losses. So as motors produce current, they get hot. And really a lot of the limitations in motors have to do with how hot they get. So we want to be able to model the thermal properties of the open source leg. And finally, after all this modeling, is the actual physical design of the leg, where we actually pick out components and we lay them out in the best possible way. And I would like to point out that these last 3 steps are very iterative, and it's a constant battle, push and pull of finding the best compromise between the smallest possible physical design and the best torque, speed, and voltage current operation. So kind of taking a look at the final design. So on the left, we have the knee, and on the right, we have the ankle. And if we take a look inside, you can see kind of the guts of the leg. And one thing I'll point out, because we're using those high torque motors, we have a transmission ratio of about 50:1, which is 2 to 5 times lower what other prosthetic legs have used. And this is good because lower transmission ratios improve efficiency, they improve mass, and they improve audible noise. So our transmission is quieter than other transmissions. And the transmission that we use, because it's a low transmission ratio of 50:1, is we have this 3-stage belt drive transmission on the knee. Let's see. We have a 3-stage belt drive transmission on the knee, and on the ankle, we have a 2-stage belt drive with a 4-bar linkage. And here you can kind of see what the belt drive looks like as the knee is moving. So you can see all 3 stages rotating. And we also have, I didn't mention before, but we have a battery compartment both in the knee and the ankle to allow people to test untethered from batteries external to the leg. Now moving away from the design and looking at benchtop testing to really characterizing the performance of the leg and how well it performs, I ran a series of tests. This is just some of them. First was looking at how well we can perform in position control. So on the left, you see, on the top, you see the knee moving to different positions, and on the bottom, you see the ankle moving to different positions. And so these are just traditional step response tests. So we want to see how quickly and how well we can get to a desired position. And then I also ran in frequency response. So this is a different type of test where the knee and the ankle are commanded to track a high frequency noise signal. And using that, we can characterize the frequency response or the Bode plots of this system. And the main takeaway from this testing is that the knee and the ankle have a bandwidth of between 10 and 20 hertz, which is higher than some other prosthetic legs. And it's about 5 times higher than the bandwidth of the human body. Which means that really the takeaway here is that we are more than capable of recreating the motions and in the relevant frequencies of human walking. And then I ran similar tests with the current controller. These aren't as exciting because there's no motion, but this is the same kind of work where I did step responses for the current controller and bandwidth testing for the current controller. And as I mentioned before, ultimately what we care about is not overheating the motor. So I ran an experiment. I did lots of thermal modeling to understand and really model the thermal properties of the open source leg. And the nice thing about this modeling is that we can treat a thermal model very similarly to an electrical model. So here we're taking the thermal model and turning it into an electrical circuit. And the analogy between the thermal domain and the electrical domain is voltages or temperatures become voltages and heat flow becomes current. And in this case, heat flow, this input heat flow, is the power loss due to the current produced by the motor. So this I squared R is the current that the motor is producing multiplied by the resistance of the motor that produces the thermal power loss. And then we can model that. And so what we did is we ran an experiment. So here we see 2 videos. These are thermal images of the knee where I commanded a constant current. And over about an hour and a half, I measured how hot the motor winding got, as well as how hot the housing of the leg got. And the goal was to characterize and find these 4 purple parameters. So these 4 parameters are thermal resistances and thermal capacitances of both the motor and the housing. And the way we did this is using these thermal images, we measured winding temperature in blue. We measured housing temperature. We also knew ambient temperature. And using these measurements, created an optimization that would find these 4 parameters. And so that looks a little bit something like this. So these blue and yellow lines are just the thermal data from this video that you're seeing. And then I performed an optimization where the goal was to recreate these lines in a computer model. And so here you can see kind of what that optimization looks like, where in the beginning, when this restarts, you'll see that the fit is pretty poor, and over time it gets better. And so using this model, we're able to essentially simulate any type of activity and see how hot the motor would get and how long it can operate for. Kind of moving on to getting closer to real testing on people, we decided to use impedance control for the open source leg. And in the human body, impedance is a powerful biomechanics tool because it describes how the body reacts to disturbances, and as well as how energy is stored in joints and how energy is transferred from the ground up through your body when there are perturbations. And essentially what impedance is, it's this dynamic relationship between the input kinematics and the output kinetics. And what I mean is it's the relationship between positions, velocities, and torques. And our group, as well as other groups, have spent a lot of time characterizing and measuring the impedance of the human body. And so for the ankle, for example, we can approximate the impedance of the human ankle with a stiffness and a damping term. And it also, in many cases, an inertia term. But in general, when I talk about impedance throughout this presentation, just think stiffness and damping. So just think of springs and dampers. That's really all I mean when I'm talking about impedance control. And so how do we transfer this impedance model into a prosthesis? So what we do is we have this equation, which basically says that the torque that the prosthetic leg has to produce is a function of stiffness multiplied by a displacement and damping multiplied by a velocity. And so essentially what the prosthesis is behaving is like a damp spring. So this is a video that my lab mate Eunhee took of the knee operating in impedance control. And as you can see, as he interacts with it, it kind of returns to its original position with a spring-like manner. And so using this controller and kind of splitting up the gait cycle into many phases, we're able to recreate natural walking patterns. I'll show you kind of what that looks like. So in this video, you can see my very first steps with the open source leg. This is only using the knee. And here it's just very basic. I just want to make sure that this thing can carry my weight, that it will switch between different conditions. It knows when it's in the air and when it's on the ground. Then the next day, I got a little bit more adventurous and started walking on the treadmill, still with just the knee. But as you can see, this is still a very unnatural walking pattern. But over a couple tuning sessions, we can get to a much more natural walking pattern. And so this is using impedance control, using multiple, basically splitting up the gait cycle into multiple regions and doing a lot of tuning. So this was about 24 parameters or 24 knobs that I had to tune, as well as 7 transition criteria that I had to tune to get a natural walking pattern like this. And I want to point out that I did a lot of testing on myself beforehand. So I'm wearing this adapter that's basically a cast that simulates myself having an amputation. So I did a lot of this testing on myself first before moving on to testing it with actual patients. But here's a picture of our first patient, kind of getting her set up. And basically what I did is I took the controller that I implemented for myself and applied it to her. And whenever I tuned it on myself, it required multiple days of tuning. But starting with my parameters and moving it onto her only took maybe 30 minutes of tuning to get it to the point where she could walk naturally. So that looks a little bit like this. I think. I want you guys to hear what it sounds like when people are walking. But as you can see, she has a pretty natural walking pattern. This was after about 30 minutes to an hour of walking with the open source leg. And then our collaborators in Chicago at Northwestern University have sort of taken the open source leg and kind of run it through more rigorous testing with patients. So they've had multiple patients. And in addition to walking on level ground, if you see on the right, they have this circuit that lets people walk up and down stairs as well as up and down ramps. And so they also use impedance control. So they use the same impedance control that I showed before, and they use a combination of hand-tuned controllers like I showed, as well as some more biological inspired controllers. And the controllers, and this group is one of the few groups that does both mid and high level control. And so we're, as part of this open source leg project, we're actually going to open source some of the high level controller to begin helping other groups start to integrate mid level control with high level controllers. So kind of to close this off, the contributions of the open source leg so far is that when we were working on this leg, we were the first bionic leg to use these drone motors, which allowed us to have a much lower transmission ratio. Since we started working on the open source leg, other groups, including Bobby's group, who's on my committee, and other groups at MIT, have also begun to use drone motors, both on prosthetics and exoskeletons, and which is, I think, a good sign for the field that these motors have a lot of potential for future use. And because we use these motors, we're also able to save a lot on mass. So compared to similar devices with similar performance characteristics, the open source leg weighs 20% less. And we were able to get it down to $10,000 to $30,000, which might seem like a lot, but for example, a single bionic ankle that's available on the market costs closer to $100,000. So this is $30,000 for both the knee and ankle versus $100,000 for just the knee or just an ankle. And really the main contribution was that we basically open source everything. We open source the hardware, the software, the controls, as well as all the clinical data that we've collected. We have open sourced that. And the goal was, as I mentioned before, to unify experienced researchers and to allow new researchers to come in. And part of the way that we've done that, so this has been myself, in addition to many other people in the lab, I have lots of lab mates to thank for this, is we've done a lot of live demos at different conferences, at different events. We have a website, opensourceleg.com, where you can find all the parts to build this and all the instructions to control it. And I think two of my favorite memories of like going out and sharing the open source leg on the bottom left, that's me with astronaut Scott Kelly. And as many of you know, in a previous life, I was an aerospace engineer, and astronaut Scott Kelly asked if he could walk on my leg, and he was one of the first people outside of our lab that I was like confident enough in letting him walk on the leg. And so that was like a cool combination of my previous career and my current career coming together into one. And on the bottom right, that is the open source leg on display at the Museum of Science and Industry in Chicago. So it was really cool to get to go to a museum and basically see my PhD on display. So we, myself and as well as many other lab mates like Unki, Kim, Ennis, we've all spent a lot of time over the last 2 to 3 years really trying to get the word out, trying to disseminate the open source leg and really unify the field. And I think we're doing a pretty good job. So in the last 2 years, these are all the institutions that have begun using the open source leg. This is a combination of both old and or experienced and new researchers. So universities like Northwestern and Carnegie Mellon have a long history in working with bionic legs. And these groups are actually replacing their old system with the open source leg. And then there's groups like University of Washington and Imperial College London that have done a lot of modeling and simulation work, but didn't have a system to actually prove their work with. But now they're building the open source leg. And hopefully over the next couple of years, we're going to start to see lots of results from different institutions using the open source leg. So kind of moving on to a slightly different topic. This is work that builds off the drone motors that the open source leg uses. And basically, because these drone motors are only now beginning to be used in bionic systems, they haven't really been tested and they're not really, their performance isn't very well understood. So I ran a series of experiments to begin to understand the performance of these systems, especially with transmission ratios. But I'm really only going to focus on one of them for this talk, which is characterizing the impedance controller in open loop. So as I mentioned before, this is the type of control that a lot of bionic systems use. So this is impedance control, where what we care about really is commanding a stiffness and a damping value. And as I mentioned, because we don't have torque sensors to measure this torque value, these systems are typically implemented in open loop, where we don't know that the actual output torque. We can estimate it, or we can have a model and based on the motor current of what the output torque is. But we don't actually know with an impedance controller for sure what the output stiffness and damping values are. So we might think we're commanding a stiffness of 10 Newton meters per radian, but we might actually be commanding a stiffness of 8 Newton meters per radian. And in some cases, that error matters, especially in research settings. So the goal of this study was to use system identification techniques to identify the output impedance parameters of these actuators used in bionic systems. So really, I want to measure the stiffness and damping values of these systems. And so I did this with 2 different experiments. The first was using the motor on the open source leg, so just the motor on its own. And then the next study was basically that same motor, but with a transmission attached to it, so with gears attached. And I used a 6-to-1 motor and a 9-to-1 motor. And what that experiment looks like is you have 2 motors that are connected. One motor that I'm calling the driven motor is operating under impedance control, so it's commanding a stiffness and a damping value, while at the same time a separate motor is providing position perturbations. And these position perturbations are white noise perturbations similar to those that I showed earlier during the OSL testing. And while the motor is being perturbed, we have a torque sensor in between that is measuring the response torque of these perturbations. So we have a torque sensor here in this benchtop testing, but normally under normal operation, we wouldn't have a torque sensor. So in this test, even though we have a torque sensor, we're not using it for control, we're only using it for measurement. And so in this case, this is a video of what that experiment looks like. The input to our system is our positions, velocities, and accelerations, and the output is a torque. And so using this input and output information, we can do our characterization. And what we want from this characterization is we want this model. So we want this transfer function that converts positions to torques. And that is using this equation where basically it's inertia, damping, and stiffness. So we want to actually calculate these three I, B, and K values. So we use a method called Blackman-Tukey spectral analysis that takes the perturbation information and analyzes it in the frequency domain, and it gives us a frequency response or Bode plot of the system. So this is a non-parametric system identification technique. So we have this frequency response, we have this plot, but we don't actually have the I, B, and K values that we want. And so in order to go from this G spa, what I'm calling, so this transfer function from the spectral analysis to this transfer function of this impedance system, well, I implemented a similar optimization method as before. And basically what the goal of this optimization is to minimize the difference between the frequency responses of this blue system and a system of this form while we optimize these I, B, and K values. And so this optimization looks something like this. And so the goal is for the yellow line to match the blue line as well as possible. So the results of this testing, let me walk you through some of these plots. So here we have output stiffness versus desired stiffness. And on the bottom, we have output damping versus desired damping. This is for the direct drive controller, so without a transmission. And the black dashed line is essentially denoting a perfect relationship between the desired stiffness and damping and the actual measured stiffness and damping. So the closer that we are to this black line, the better we are at doing open loop control. And so we can see with just the motor, we basically fall directly on that line. And that makes sense because there is no transmission. And so motor current does a very good job of approximating motor torque. But as we add a transmission, so this is for the 6-to-1 transmission, we begin to see losses where the output stiffness does not match the desired stiffness as well. And with the 9-to-1 motor, we see these losses increasing. And so with this information, as you can see, one thing I want to point out is that even though there are losses, these losses are still linear. So we can provide a very simple correction factor once we've done this characterization to get more accurate open loop control. And this is simply done by basically just multiplying the desired value by a correction factor. So in gray, if you can see here, is the same data that I showed before, but if you implement a correction factor and rerun this experiment, you can get much closer to the dashed line, to the ideal relationship between desired and output stiffness. And so using these correction factors, which was just a constant, we can decrease our errors from 26 to almost 0% for the 6-to-1 and from 42 to 3% on the 9-to-1. So some of the takeaways here is that a motor without a transmission is capable of doing accurate open loop impedance control, but that adding a transmission creates a mismatch between the desired and the actual output impedance. But that's okay because we can account, once we've done our characterization, we can account for those losses and improve impedance control. So the main contributions here is that I formally outline methods in the paper that I'm working on to actually characterize this. So hopefully other groups can in the future also characterize our systems thoroughly. And I investigated the effects of transmissions and showed how even though we have open loop impedance control systems, we can still have accurate output impedance. And something I want to mention is that part of this is possible because we're using these drone motors that have low transmission ratios. This would be harder to do with motors that have higher transmission ratios. And then now kind of looking at a different side of bionic systems, focusing more on the user perspective, something that I'm interested in is understanding how well people can perceive changes in the assistance that an exoskeleton is providing them. And so that was the purpose of this study. It was looking at specifically at damping perception. In this work I published, presented at a biomedical engineering conference and came in second place in the student paper competition. And it was also accepted in a journal on neural systems and rehab engineering. So kind of going back to impedance, our lab over the last 5 years and even before I joined the lab and even when Elliott was a grad student has focused a lot on different aspects of impedance. So for example, we focused a lot on measuring the impedance of the human body during walking, both for healthy patients and for patients with stroke, for walking and for running. We've also looked at impedance regulation. So how well can somebody actively change the stiffness of their ankle? And what I'm particularly interested in is impedance perception. So how well can somebody perceive the changes in the stiffness or the damping properties of not their own body, but of an exoskeleton or of an external device that's attached to their body? And there's a couple reasons why I'm interested in perception in particular. And one is on the implications that perception has for the sensory motor system. So there's kind of this idea in the sensory motor system that if you can sense it well, then it matters. And an example of that is with touch. We are very good at discriminating touch with our fingers, much better than we are at our back, for example. And that, for many reasons, it shows that touch is super important at the fingers because we do a lot of manipulation and we require a lot of dexterity at our fingers, but not necessarily so much with our back. And there's also been shown that being able to sense changes in different properties like positions and torques can help prevent injuries, especially at the ankle. So there are sensory motor and biomechanical impacts to being able to sense changes in properties. In addition, with locomotion, being able to sense properties in the environment, and when I say the environment, it can either be the ground or it can be an exoskeleton, helps you interact with that environment. And there are also potential applications of transferring this knowledge of perception from a purely scientific experiment into bionic systems. And this has been done a little bit in the upper limb. So taking force perception data and torque perception data and applying it to upper limb exoskeletons. But the goal of this study was specifically to quantify changes, to quantify how well people can perceive changes in damping. So in this B value, both at the knee and the ankle. And during my master's degree at Northwestern, my first study was looking at stiffness perception. So looking at how well people could perceive changes in stiffness. And this study kind of builds off of that and kind of completes impedance perception by looking at both stiffness and damping. So the setup that we did here is we didn't have an exoskeleton for this study, but we had this big dynamometer, which we can essentially control it to behave like an exoskeleton. So on the left, we have people seated with their ankle connected to the dynamometer, to the motor. And on the right, we have subjects seated connected with the dynamometer on their knee. So this dynamometer, we controlled it not with impedance control, but with admittance control, which is essentially the inverse of impedance control. So here we're still commanding stiffness and damping values. And what we did is we implemented a psychophysical method that would help us understand how well people could sense when I change the damping values of this controller. And these psychophysical methods have been used a lot in other fields. So understanding how well we can sense changes in sounds or in visual cues as well as in touch. And so kind of what this experiment looked like is at the beginning of the trial, subjects would interact with this controller and it had a certain damping value. And after about 8 seconds of them interacting with it, here's a video of somebody interacting with the motor, I would change the damping value. So I would either increase it or decrease it, and in some cases I would keep it the same. And then I would ask the subjects after another 8 seconds, did the system increase damping or decrease damping? If they were correct, then the next trial, the two damping values would get closer together. If they were incorrect, then the next trial, the two damping values will get farther apart. So essentially this experiment gets harder the better you do, and gets easier the worse that you do. And so we would basically repeat this process over and over across both the knee and the ankle and across multiple damping values. And we used a method called the weighted staircase method that converges to a number called the Weber fraction. And the Weber fraction represents the percentage in a stimulus that you can sense reliably. So in this case, the Weber fraction represents the percent change in damping that people can perceive with 75% accuracy. So a Weber fraction of 0.1 means that if I change, that I need to change damping by 10% for you to be able to perceive that change. And the smaller the Weber fraction is, the better you are at perceiving the number. because it means you can perceive a smaller change in that parameter. So this is what the results of this experiment look like. So here we have web refraction plotted against damping value across multiple damping values. And the main takeaway here is one is the overall shape of these curves, which was expected. This is fairly standard for in other psychophysical experiments. But what this shows is that at low damping values, we have worse perception because we have a higher web refraction. But as you increase damping, our perception of changes in damping improves and approaches an asymptote. And this asymptote is normally what's considered like the peak performance point or the best perception point. So many studies will they won't report this whole curve. They'll only report the web refraction at the highest value. So in this case, our web refraction shows that people can detect changes in damping of 12 to 13%. So if we take these 2 points, the same data, and we plot it in a bar graph, we can compare our results to results from other studies. So here we see the damping data for the blue and the yellow plots are the same data that I showed before. And then in gray, we have damping perception at the elbow. So this was done by a different group. We have stiffness data. Once again, the blue and the yellow plots are from my master's work, and the gray is from a different group. And we also have torque perception data, all of which were from a separate group. But the main takeaways that I want to show here is one, we're better at torque perception than we are at damping or stiffness perception. And that makes sense because in order to perceive changes in stiffness or damping, you need both torque information and position or velocity information. So you have to be able to perceive changes in 2 parameters to perceive changes in stiffness and damping. So in a way, you have noise both from torque and positions and velocities that have to be integrated in the sensory motor system to perceive these changes. So one, we're better at torque perception. The second takeaway is that stiffness perception, the second set of bars, is approximately the same across the knee, ankle, and the elbow. But that is not the case for damping. So we're much better at perceiving changes in damping at the lower limb than we are at the upper limb. So kind of restating a lot of these things. Both damping and stiffness, the main takeaway is that damping and stiffness need to change by about 12 to 13% at a minimum for them to be perceived reliably. We have better impedance perception at the lower limb than we do at the elbow, and that impedance perception is worse than torque perception. And so like, what does this mean? The one thing I want to point out is that stiffness and damping perception were similar at the lower limb, which was a little bit surprising at first because we were expecting damping perception to be worse like it is in the upper limb. But the fact that both stiffness or damping or perception are similar, it suggests that both of these parameters are important in the lower limb for the sensory motor system. So if you're interacting with an environment, whether it's the ground or an exoskeleton, both the stiffness and the damping properties of that environment are important. And a separate point I want to make is that the field has focused a lot on investigating the effects of stiffness on walking, on biomechanics, on metabolic cost, on many different parameters related to the user. But there's been little work looking at how damping affects locomotion and biomechanics. Right? Not little work, but much less work than stiffness. And so I think this is sort of a call to action that maybe we need to focus on damping just as much as we need to focus on stiffness. And I would say that one big limitation of this study is that it was performed in a seated position. So one of the next steps is actually to perform a similar study while people are wearing an exoskeleton and walking with it and seeing how our perception changes with that. So the main contributions of this work was one is that we found a perception threshold that can be implemented in bionic systems. So an example of how this could be implemented is if you have an exoskeleton that is operating with impedance control and you want to change the parameters of that exoskeleton without interrupting or disrupting the user, make sure you're changing those parameters, that your changes remain below that perception threshold. And then the second takeaway is that this study, along with my master's thesis, completed the first set of studies that actually looked at impedance perception in the lower limb. So up until now, there was a lot of work of stiffness and damping perception in the upper limb, at the elbow, and especially at the hand and at the fingers. but there were no studies looking at impedance perception in the knee or the ankle. So this is the first set of studies. It's in a way, it's laying a foundation for more studies, a wide range of studies looking at perception in the lower limb. And we've begun to see that, especially in our lab. So with one of my lab mates, Max, who graduated last year, we basically took this work and we extended it. We extended it to amputees, and we looked at how well they could perceive changes in the stiffness of their prosthetic ankle. And additionally, other lab mates of mine are now looking at other forms of perception with exoskeletons during walking. So kind of to close everything out and to bring everything back together, the main contributions of my work were one, to develop, to test, and to really disseminate the open source leg and to begin unifying the field and expanding the field of bionics. Two was to create tools to characterize and improve open loop impedance. And in addition, I didn't really talk about it here, but I ran a series of other studies to further understand how these drone motors operate with transmissions. And finally, to really begin to set the foundation for perception studies and for more user-focused studies with exoskeletons in the lower limb. And I was able to accomplish this in multiple ways. So in terms of first author papers, between my master's and my PhD, I've had 3 first author papers published, and we're wrapping up our 4th one that will hopefully be submitted by the end of the month. And then a second author journal paper, which was that perception paper with amputees. And I've been able to do lots of other things during my PhD. So some other highlights is last year I helped Elliott develop and teach a new graduate level class that was focused on design and control of bionic systems. So a lot of the design work that I skipped in this presentation, we delved a lot more deeply into that in this class. And then I spent the last year and a half working at Google and basically been able to take a lot of the skills that I developed throughout my PhD, and they've all come together at Google. And as Elliott mentioned before, I've been very lucky to have lots of fellowships that have been able to fund my research and have given me a lot of freedom to really explore what I wanted to explore during my PhD. So I want to thank the National Science Foundation, the GEM Consortium, and University of Michigan for allowing me to have the freedom to explore during my graduate career. And I also came close to getting a few other fellowships like the Hertz, the NDSEG, and the Ford Fellowship. And finally, as I mentioned, we spent a lot of time presenting at conferences, and I've had lots of luck at conferences between student paper competitions and hardware demonstrations. So what are the next steps, pun intended, for this research? So for the open source leg, I can see a couple of different things that need to be done. One is to expand on the impedance control characterization that I did and do that with the open source leg. So I did it with the motor that the leg uses, but the next step is to do this with the entire system, with both the knee and the ankle. And in my work, I've laid out how to do that. And from there, we can do more biologically inspired impedance control. So taking some of the other work that my lab mates have done, understanding the impedance of the human body and creating controllers that recreate that impedance. And this was originally going to be my final study, but due to COVID and other circumstances, we couldn't test on humans, so we kind of shifted things around a little bit. And then the next step after that is to basically take the top control systems, the top high-level, mid-level control systems, and really test them all, pit them head-to-head to each other, so that we can begin to understand the pros and cons of different approaches and understand where they flourish, and understand maybe how we can begin to combine different types of control systems to come up with better control systems. So up until now, no one has really been able to compare control systems, in part because everybody has different hardware. So now that groups are beginning to all have the same hardware, we can really begin to do these comparisons. And next steps and recommendations for the field in general is one of the challenges when we were designing the open source leg was comparing our performance to other devices was very difficult, because very few groups really lay out the specifications of their systems, and they also don't necessarily talk about all the characterization that they did. So one thing that I would like to see is more transparency from other designers. And in my thesis, I kind of lay out the different types of characterizations and the different types of specifications that should be reported. I would like to see more, and we're starting to see more use of high torque drone motors with lower transmission ratios. So I think it's a great sign that not only the open source leg, but other groups are starting to go in that direction, and there's lots of benefits there. And so I would like to see more of that, which will require a lot more characterization to really understand these systems. And finally, I think a huge area of research that I'm really excited about is looking more on the user side of things. So understanding, kind of expanding some of my preference work into other activities like walking, running, going up and down stairs, as well as looking at what do people prefer and understanding how do people react and behave with different types of assistance and different types of control systems. So when I started my PhD, I was super excited to spend like the next 5 to 6 years in Chicago. Little did I know that my PhD was going to take me all over the country. So I spent 2 years in Chicago at the Center for Bionic Medicine and at Northwestern University. Then I spent 2 years at the University of Michigan helping Elliott start a new lab there. Then I spent almost a year in California working with the Google team. And due to COVID, I spent the last 6 months back home. So it's been a wild ride. But I want to say that all the people in these pictures and the people who are not in these pictures who I've met, the mentors, the coworkers, the friends, the lab mates, have meant the world to me. This PhD would not be possible without all of you. In particular, Elliott, thank you so much for being a great mentor, for trusting me, for letting me, take the reins and really make my PhD what I wanted it to be. Thank you to my committee, especially Luke, who's been very involved in the Open Source Select project, as well as Bobby and Ram, who have provided really good insight into my work. And finally, thank you to the Azocar lab, as I've been calling them the last couple of weeks. It's been awesome to get to finish out my PhD at home with my family. The last couple of months have been a lot of work and have been really hard, but they've kept me healthy, they've kept me sane, and I wouldn't be able to do this without them. So thank you, everybody, for listening to my talk.
Great. I'll give you a virtual round of applause. Now we can take questions from the audience. So maybe I will start with one to kind of kick things off, and then I'll hold the rest of my questions. So somebody be thinking of their next question. So my question for you is, do you think that the damping perception from the knee and the ankle are the same or different? So both of your studies show slight differences in the response, but then also there's uncertainty in those metrics. So do you think those are different or the same?
As in, are we better at one joint than we are at the other?
Yes.
So in my work, no, we didn't see any differences. I think if you were, and I think part of it was the limitation is that we were in a seated position. I think if you were to start doing this testing with an exoskeleton while people are walking and doing more dynamic tests, then you can really start to tease out the differences. And I think you would end up seeing, this is a hypothesis, is that you would end up seeing better perception at the ankle than you would at the knee. But that's something that hasn't been tested yet.
Hey Alejandro, can you hear me real quick?
Yeah.
Hey, this is Mal. Congratulations on the defense. That was pretty awesome. I like the presentation. Just to follow up on Elliott's question real quick, are you aware of any impedance perception tests or experiments done on athletes? Would there be any difference between an athlete and a non-athlete person?
So, no, not impedance perception. There have been other studies that have looked at like perception of positions and torques, and there is in some cases better perception for athletes, which makes sense. They need to be very aware of their body, of the dynamics of their body to do what they do, and that was actually something that Elliott and I talked about early on. Was should we recruit different populations? We thought about recruiting athletes from like the Northwestern basketball team. To really start to look into that, but we decided to have the study be a foundation, and then from there build from there. And another thing sort of related to athletes is that being able to perceive, basically the athletes that are better able to perceive changes in ankle position are less likely to get injured. So there is a big component of perception when it comes to performance and injury prevention.
Thank you.
Hey, Alejandro, thanks for the talk. It was great. If you hear music in the background, sorry about that. It's Friday evening here. Yeah, I had a question for you. So you mentioned that the OSL is about 20 to 30% lighter than other commercially available prostheses, and about 4 times lighter than, or 4 times heavier than a passive one. How does it compare to a biological limb, first of all? And then the second part of my question, if it's significantly heavier, does that affect the hip joint in terms of wear and degradation in general?
The open source leg is slightly lighter than the biological limb, but that being lighter isn't necessarily enough because prosthetic limbs are not anchored to the body like your actual limb is. It's not anchored through bone. And I think the second part of your question was, how does this affect the hip?
Yeah, so that was mostly if it was much heavier than the biological limb.
So we actually haven't looked at hip kinematics with the open source leg in general, but other groups have looked at hip kinematics with prosthetic legs, and at least with bionic ankles, hip kinematics are more closely returned to normal when you have that additional power that you wouldn't have from a passive system.
Yes,
Yeah.
thank you.
Yeah.
Azocar, great talk. Love to hear it. Really just have a small clarifying question for the work that you did characterizing the motors. You showed notable error increase as you increased the gear ratio for stiffness, but damping was relatively low throughout. And so can you maybe explain or just like maybe reiterate again why you think that was the case?
Yeah, so I think part of that is, so part of those losses are due, one is just to transmission losses, but so these motors also had some backlash. And I think a lot of the reason why you see those losses amplified more in stiffness is because because this was a very high frequency test that we were doing with lots of changes in direction, the backlash, as you change direction, the backlash affected what the motor was seeing as well as what the motor was outputting. And so that backlash impacts more the stiffness and the position properties of this testing.
Got you. Thank you, doctor.
And I guess kind of related to that, in some of my other tests where it was where we were operating in steady state, where there weren't any changes in directions and where backlash wasn't present, then we saw much lower losses. So part of it is due to the types of tests that we ran, but in actual operation, we're never running in steady state, so it's important to understand these losses.
We have a question from the chat, Alejandro. Michael Gonzalez would like to know, what is the biggest challenge that you overcome, either technical or theoretical?
The biggest challenge that I've overcome? That's a great question. I think probably is in like design and mechatronic skills. When I first came into the lab, I had very little in terms of skills in terms of how to design these systems that require high tolerances, that require a lot of interaction with the human body. So building those skills and understanding how to make these trade-offs between the transmission ratios and stiffness properties of the prosthetic leg. So that is a combination of technical physical design as well as more theoretical simulation and modeling based. But I would say that was what took me the longest. Thanks, man.
So I have another question from the chat. This is from Niraj. He says, sorry if I missed this, but is the characterization for impedance control packaged for other users of the open source leg?
So we are in the impedance control work that I showed. That was only the motor. So it didn't include the actual transmission of the open source leg. We are gonna publish the correction factors and how to improve impedance control. But basically the next step is to run the study again with the open source leg, and that will become part of what's available for others to use.
I got a question, Alejandro. Great talk, by the way. Great to see you. Maybe kind of a novice modeling question, but you were talking about the bandwidth and looking at the different Bode plots, and you mentioned that it was far above the bandwidth of the human body. So I wanted to clarify and ask, is when you're talking about the bandwidth of the human body, that would be governed by like mass, essentially, of like the different body segments? Is that correct? And is there like an accepted number for that bandwidth that the field would say like the bandwidth of the human body is like 4 hertz or 5 hertz or
That's a great question. So typically, the way I calculated bandwidth and the way other groups have calculated bandwidth is if you look at biomechanical data, so if you look at the positions of the knee or the ankle during walking, and you convert that time domain data into the frequency domain data, you look at where approximately 70% of the power of that frequency spectrum is contained. And for the knee, that's at about 2 hertz, from 0 to 2 hertz. And for the ankle, that's about 0 to 4 hertz.
Okay, awesome. Thank you.
Hey, Alejandro, I had a quick question. First of all, awesome presentation. It was so cool to see everything come together. I love the vision of the open source leg, and I'm wondering if you think there's a risk that 5 years down the line, it's obsolete, and the kind of its point of serving as like this general use platform is limited, or if that's not the case.
There's no way that's going to happen. No, I would say, so part of what we're doing with the open source leg is, so we have, as part of the website, we have this forum where basically other researchers who are using the open source leg can make improvements and suggestions. And so we hope that the leg over time will continue to improve as other groups kind of come in, start using it, and provide suggestions. And we've already had lots of great suggestions over the last year from users. So I'm hoping, and I'm sure that 5 years from now there will be new motor technology, new battery technology. But I'm hoping that our lab and other labs can continue to implement those improvements in the open source leg.
Awesome, thanks.
Any last call for questions?
Hello, hi Alejandro. Well, thank you so much. Your work has been super beneficial for me in this field. I have been one of the few who has benefited from the prosthetic leg, and it works like a charm. I'm still learning about it, but I would definitely recommend it. And so regarding the characterization of the impedance for the OSL, I wonder if you have a vision on characterizing also the role of the tension within the belts. We have seen completely different performances depending on how you tune a simple knob. And so I wonder, what are your plans to characterize this behavior?
Yeah, so that's actually part of the reason why this impedance characterization hasn't been completed is because it is a pretty big undertaking to really characterize it well. And the idea is, so we have that dynamometer that I showed for the damping study, is we can mount the open source leg to that and perform different studies. And the idea is to do it with different stiffness and damping parameters, as well as with different tensionings. And so we can understand how increasing tensioning improves or degrades impedance control. And in general, not with impedance, but with torque control, I have found in some of my other work that torque control efficiency is improved as the tension increases. So I think there will definitely be differences, and those will have to be accounted for.
Thank you.
I have a couple questions from the chat. This is from Selena Statler. I apologize if this is already discussed, but is it repairability, recyclability being considered at end of life?
That is for the open source leg. That has not been considered. Thankfully, most of these parts are aluminum, So they, once if it breaks or if it needs to be discarded or replaced, they can be recycled. So that's been one of the benefits, is that I would say 80% of the open source leg is recyclable parts.
Great. I got a couple more that are coming in from the chat. So for tuning the leg for different individuals, is there any parameterization based on body proportions, physical ability, etc., or is it just starting from what you got working for yourself and then tweaking those dials?
So all it did start from where I tuned myself, but these parameters I had already tuned to be basically weight normalized, which is what made it much easier to basically go from my parameters to somebody else's parameters. The work that they do in Chicago is similarly weight normalized, but they also have some parameters that are independent of the user and basically use other modeling techniques to tune.
Okay, and I have one more from the chat. Says, are you thinking about eventually commercializing the open source leg?
No, we're not. We have talked to a couple different companies to help us build and share the open source leg, but we're not looking to make a profit from this.
Last call for questions. Okay, thanks everybody. The committee and Alejandro, we're going to create a breakout room and then we'll grill them for an hour. Thanks again, everyone.